Hi everyone. So in this video series we're going to start talking about algorithm analysis, specifically with regards to big O notation. So in this first video I'm going to talk about what we mean by big O notation and kind of walk you through an example of a simple algorithm and express it in terms of big O. So before we begin, I'm going to just talk a little bit about why we would use big O. Big O is a way to predict the performance limits of an algorithm. And if we know how an algorithm is going to perform, we can better classify and compare it with other algorithms based on performance. See, algorithms are, it's not like if we wanted to compare the performance of two cars, for example, we might put them side by side on the road and race them to get a speed comparison, or maybe compare the gas mileage in some way. But algorithms are different because they're dependent upon the machines that are running them. So we need to come up with a way that will assess the relative performance of an algorithm regardless of the machine and the specifications of the machine that they're running on. We are especially interested, when we're talking about big O, we're especially interested in what happens when algorithms are forced to process very large amounts of data. We're interested in what happens when the input of the algorithm, and by input I just mean the data that the algorithm is supposed to process, when that input gets very, very large. Okay, so let's begin. We're going to just a hypothetical scenario here. We have two algorithms. Algorithm A solves the problem, whatever generic problem we're talking about. Algorithm A is going to solve that problem in 10 steps, okay? And algorithm B will solve that same problem in 5 steps. So which algorithm is faster or more efficient or better? This is kind of like asking how long is a piece of string, okay? You can't really say, because I failed to mention that algorithm A, which solves the problem in 10 steps, is going to be running on this state-of-the-art supercomputer in some top-secret research facility somewhere. And algorithm B, which solves the problem in 5 steps, is going to run on this vintage 1980s, 1990s computer. Okay, so it goes without saying that algorithm A, even though it's twice as many steps, it's going to run way faster because of the machine that it's running on. So that's an example of why we use big O to compare algorithms, because that takes this out of the equation. Whether we're running it on a machine like this or a machine like this or anything in between, it becomes a non-issue when we express the algorithm's performance in terms of big O. Okay, so before we really get down to this, I want to talk about the notion of a basic step. And this is going to bother some of you, especially if you've taken a math class recently, which probably many of you have. And in math, we're told to be very precise and every step counts. And in this, in analyzing algorithms, you kind of have to throw that thinking out the window. Let me give you an example here. So I have a basic algorithm which we'll say starts below this line. Here's a little bit of preliminary. I'm creating an integer with a maximum value called max and putting a 5 in it, and then I have an array of numbers initialized to 5 elements, and there they are. Okay, so here's my algorithm below this line. We've got a little bit of setup. I'm going to start with a loop counter, which I'm calling counter, and then I have a sum variable. My algorithm here is going to loop through the array called numbers and add up all of the numbers. That's it. Very simple little algorithm. So we have a couple of steps here with the variable initialization. So we'll say that's 2 steps. And then inside of the loop, I've got another 2 lines of code, which is just our calculations, obviously summing up the numbers, and then our loop counter increment. So that's another 2 steps. So we can say, all right, our algorithm has 4 steps. 4 steps total. Now we have to also understand that this loop is going to run 5 times. So that's really 10 steps because it's 2 times 5, but I'm getting ahead of myself. So those are the steps involved in this algorithm. Now the thing is, I'm getting really nitpicky here, and it's pointless because there's this issue again. What are we running this algorithm on? Is it this one? Is it the old junky computer? So then it kind of becomes irrelevant as to how many steps. Oh, is it 4 steps? Is it 5 steps? Is it 10 steps? So that's what I mean by you have to throw this thinking about being very precise out the window, because it doesn't matter when we're talking about algorithm analysis for the most part. So let's just reduce this to the bare minimum. We're going to simplify it. Let's just say that these 2 lines in aqua, those 2 steps we talked about, let's just say that's one basic step. It's the setup of the algorithm, the initializing these variables. We're just saying that's one step. And then these 2 lines inside of the loop we'll say are also just one step, even though it's 2 lines of code, 2 calculations going on. Again, we're not going to nitpick. It's just one basic step, which we'll call the calculations. Okay, so I have one step outside of the loop and one step inside of the loop for the sake of this discussion. Okay, so we would say, if I want to express this algorithm mathematically, I would say this algorithm performs 1 plus n basic steps where n is the size of the numbers array. Okay, that makes sense. This is one step. It's just going to go once. So we have the 1 plus. This 1 refers to this basic step that we talked about. Now the loop is going to go max number of times or 5 times, or specifically the number of elements that are in the array. Okay, which we're calling n here. N is the number, the size of the array, all right? So this basic step is going to go 5 times. So it's 1 plus 5. This thing is going to run in 6 steps, but it's really the 1 plus n, where n is the size of the array, all right? So we already said that this right here, this code would execute in 6 basic steps. Now, let me ask you this. If we changed max to 5,000 and we had an array of 5,000 elements, would that 1 really matter? Then this would execute in 5,001 steps. Okay. My point is, when numbers get very large, in this case, like in this case, in this algorithm, when that number gets very, very large, that plus 1 becomes absolutely negligible. And I had mentioned before that with Big O, we're interested in what happens when the input into the algorithm gets large. And the input into our algorithm is the array. It's not like a cin where the user's typing in. That's not what we mean by input here. We mean the data that the algorithm is working on. That's the input into the algorithm. So we're interested in what happens to performance when inputs get very large. And so that plus 1 is not even worth mentioning when we're talking about this. So again, you have to abandon your need to be very precise that you've picked up in your math classes throughout the years when we're talking about this. It's almost like just getting down to the bare minimum. Okay, so with that in mind, because the 1 is negligible, we're just going to drop it. We're just going to throw it out the door because it doesn't matter. Okay, so we would say this algorithm performs n basic steps, where n is the size of the array. All right, so expressed in Big O notation, we would say this algorithm is in the big O of n, or we would express it like this, O with an n in parentheses, okay? So that's your first algorithm expressed as Big O notation. We would also say this algorithm executes in what we would call linear time. And on my next slide here, I have a picture, okay? The green line here is linear time, okay? That's O to the ON, all right, that's the linear time. And that means that, you know, if n is, if we increase n by 100 times, then the performance is going to increase by 100 times. The performance increases linearly, or the time to execute, I should say, is going to increase linearly. It's directly proportional to the size of the array. If the array has 5 items, it's going to take a certain amount of time, but if it has 50 items in it, it's going to take 10 times longer. That's what we mean by linear time. So in the next videos, I'm going to break this up, and we're going to look at some of the algorithms that we've already talked about in this class, like the bubble sort, the selection sort, the linear search, and the binary search. And we're going to look at them in terms of their big O notation. So that's what's coming.